Hello and welcome to this calculus video. Today we'll be talking about what the derivative tells us about the original function.
Math 112.
Many of the applications of calculus rely on using information about the derivative of f of x to derive facts about f of x itself. One of the most straightforward examples of this is that the derivative can tell you whether a function is increasing or decreasing. We know that if f prime of x is positive, then the tangent line to the curve has a positive slope, so we would expect f of x to increase if we increased x by a small amount. Similarly, if f prime of x is negative, then we expect that f of x will decrease if we increase x by a small amount. The mean value theorem allows us to prove a precise version of this idea. The increasing-decreasing test says that if f prime of x is greater than 0 on an interval, then f of x is increasing on that interval, and if f prime of x is less than 0 on an interval, then f of x is decreasing on that interval. The reason this is true is because the mean value theorem tells us that the average rate of change over a region is equal to the instantaneous rate of change at some point in that region. If that instantaneous rate of change is always positive, because f prime of x is greater than 0, then the average rate of change is positive, and so f of x goes up across the region. Similar reasoning applies when f prime of x is less than 0. This allows us to find regions where f of x is increasing or decreasing. For instance, if f of x is 3x to the 4 minus 4x cubed minus 12x squared plus 5, then its derivative is 12x cubed minus 12x squared minus 24x, which equals 12x times x minus 2 times x plus 1. To find the regions where the derivative is positive or negative, we find the critical numbers of f of x, which is when x is 0, 2, and negative 1. Because f prime of x is continuous, we know that f prime of x can't change sign except at the critical numbers, so we can determine whether it is positive or negative by plugging in a value in between, or by examining our factorization. We can draw our findings on a number line. This is called a sign chart for f prime of x. We can use the increasing-decreasing test to classify whether a critical number is either a local maximum, local minimum, or neither. The first derivative test says that if c is a critical number of the continuous function f of x, then if f prime of x changes from positive to negative at x, then f has a local maximum at c. If f prime of x changes from negative to positive, then it has a local minimum. And if f prime of x does not change sign at c, then it has neither. Applying this test to the function in the previous example, we find that f prime of x changes from negative to positive at x equals negative 1, and so f of x has a local minimum there. Similarly, f prime changes from negative to positive at x equals 2, so it has a local minimum there too. At x equals 0, f prime of x changes from positive to negative, so it has a local maximum there. We can also go one step deeper and ask what f double prime x tells us about f of x. If we look at these two curves, we see that they are both increasing, but then they are curving in different directions. The way in which a curve is bending is called its concavity. If f of x lies above its tangent lines on an interval, then it is called concave up on that interval. If it lies below all its tangent lines, it is called concave down. The second derivative measures concavity for us, because a concave up function has derivatives that increase as you move to the right, i.e. f prime of x is increasing, so f double prime x is positive. This reasoning gives us the concavity test. If f double prime of x is greater than 0 on an interval I, then f is concave up on I, and if f prime of x is less than 0 on I, then f is concave down on I. An inflection point of fx is a place where f of x changes concavity, i.e. goes from being concave up to concave down, or the other way round. Also, as a technical point, we require that f of x is continuous at an inflection point. The second derivative can also be used to classify critical points. As an alternative to the first derivative test, there is the second derivative test, which says if f prime of c is 0 and f double prime of c is greater than 0, then f has a local minimum at c. Also, if f prime of c is 0 and f double prime is less than 0, then f of x has a local maximum at c. I'll add that this test requires that f double prime is continuous near c, and also, if f double prime of c is 0, then we don't learn anything. C could be a local max, or min, or neither. That's all for now, folks. Today we investigated what the first and second derivative of f tells us about f. We found that we could determine whether f is increasing or decreasing over a region by examining the sign of the derivative, and use this to classify critical points using the first derivative test. We also discovered that the second derivative measures the concavity of a curve, and that we can use the second derivative test to also classify critical points.
Math 112.